Hi everyone. This is a quick lecture video recap of oxidation states and and how they relate to redox reactions. Very generally here, I'm sorry, I'm gonna get up. I just wanted to recap a few key terms here. We refer to oxidation numbers, also sometimes referred to as oxidation states. They are like a charge. You'll see that they tend to either be integer values and they tend to have a positive or a negative values, but we don't call them charges, we call them oxidation states, or again, oxidation numbers. And they generally reflect the amount of electrons, the degree to which an atom has gained or lost electrons in order to form chemical bonds. Chemical bonds are either the sharing of electrons or the transfer of electrons, depending on whether it's a molecular compound or an ionic compound. And even when you're sharing electrons, they're not shared evenly. One atom might tend to gain more of the electrons, might be greedier for them. And so we could say, okay, in that context, it's gained some electrons if it's more electronegative than its partner. And so we'll say that it will tend to have a lower oxidation number or a lower oxidation state due to the fact that it has had a general increase in its number of electrons. We then define a redox reaction. So this is generally redox reactions are thought of as electron transfer processes, and that's true. But most formally, a redox reaction is defined as any reaction which involves a change in oxidation number. If a chemical species during the course of a reaction, if its oxidation state changes, that must have been a redox reaction, because it means that somebody gained or lost electrons in order to change their oxidation state. And then lastly here, our new definitions are oxidation is not simply the loss of an electron. Oxidation we will define as any time you see an increase in your oxidation number, and a reduction process is any time you see a decrease in the oxidation state. So oxidation numbers are handy as a way to identify redox reactions and keeping track of where electrons have or have not been transferred to. Now, there is a set of rules to follow to predict oxidation states. I've recreated that list of rules up here. They are also found in the PowerPoint presentation that I presented today in lecture, and I will be posting on the Brightspace website, but I have them up here to reference, and they're ordered by their importance. You'll see here there will sometimes be ambiguity about what the oxidation state should be, and if there is ever ambiguity, you basically go down the list of rules. These rules are more important. They take precedence over these rules. So very generally, the first rule is that a regular old element, by definition, has an oxidation state of 0. We've said that oxidation state is the degree to which an atom has gained or lost electrons, forming bonds from its free elemental state. In their free elemental state, they haven't gained or lost any electrons, so they, by definition, have an oxidation state of 0. Monoatomic ions, so single atomic atom ions, those by definition, the oxidation number is the same as the charge of that ion. So a sodium plus ion or an iron 2 plus ion would have oxidation states of +1 and +2 respectively. So these two are pretty easy to remember. This one is a little hand-wavy, but it's usually safe to assume that oxygen will have an oxidation state of -2. There's only a small handful of exceptions. Peroxides, like hydrogen peroxides, oxygen then has an oxidation state of -1, but in most of the compounds you guys will see, which are not peroxides or superoxides, oxygen will have an oxidation state of -2. Hydrogen will also usually have an oxidation state of +1. There are relatively few exceptions to that. The only exceptions to it are when it's being bound to other metals. So for example, in the substance sodium hydride, in this substance, the sodium has a +1 charge. Hydrogen is more electronegative than sodium, so the electron tends to be transferred from the sodium onto the hydrogen. So this molecule, even though it's a little strange, the hydrogen here has a net negative charge. And so this compound in this particular state, when it's bound to a metal, the hydrogen has a net -1 oxidation state. The other rules which are generally not disobeyed is that group 1 atoms, so elements, so things like sodium, lithium, potassium, cesium, francium, those all have oxidation states of +1, the same as their group number. The alkaline earth metals, things in group 2, that's going to be things like calcium, magnesium, barium, they also have oxidation state which is the same as their group number, +2. And fluorine, all the way on the far right-hand side of the periodic table, always has an oxidation state of -1. So these are all like on a specific case, these are all the element-specific rules. 3 through 5 here, those are for specific elements. Any other time there's ambiguity and you're not sure or it doesn't fall into one of these categories, that's when you resort to Rule 6, which is that the sum of oxidation numbers in a compound must be the same as the charge on that compound. If it's a molecule and it's neutral, then the sum of the oxidation states should be 0. If it's a polyatomic ion, like ammonia, NH4+, then the sum of the oxidation states should be +1. So I was going to go through a few examples of predicting oxidation numbers for using these rules. So I'm going to work through that right now. So let me write up a few examples here. So I was going to do this one. I'll do CH4Cl O-. I'll do potassium KCN, potassium cyanide, NH3, nitrogen dioxide, and then my last one I'll do is sodium nitrite. So if you want to pause the video and predict the oxidation states for each element in each one of these compounds, I would say take a stab at it, try predicting these rules, and otherwise I will work through these examples right now. So for methane, carbon doesn't fall into any of these categories. So since it doesn't fall into any one of them, it's not a free element, it's not a monatomic ion, and it's not one of the specific cases here, we actually can't predict it we have to use Rule 6. So basically we need to check the oxidation states of everything else first. So for instance, hydrogen, hydrogen we know always has an oxidation state, I shouldn't say always, almost always has an oxidation state of +1. So its oxidation state is +1. There are 4 of them. 4 of them here. Because this molecule is neutral, the sum of the oxidation states should be 0. So I get +4 from all of the hydrogens, which means that the carbon has to be -4. Should be its oxidation state. And again, you might be able to predict that. You can kind of predict that if you look at the Lewis structure for carbon, or sorry, for methane. I'll do it like this. So carbon is ever so slightly more electronegative than hydrogen, meaning it tends to pull these electrons this way. And when you're assigning oxidation states, you basically say, okay, we know these electrons should be shared, but let's say that they are not, rather they should be shared equally, but let's say they're not shared equally. Let's say, for the purposes of determining oxidation states, that they were both transferred onto the carbon. So that means that these shared electrons get pulled over here. Carbon originally was providing one of those hydrogen was providing the other, so as a result, carbon picks up a -1 oxidation state here, and then the hydrogen picks up a +1 oxidation state there. And then that process keeps repeating for all of the other bonds. So I pick up a +1 oxidation state there, and then I get 2 more from this bond. Hydrogen here picks up a +1 oxidation state. Carbon becomes a little bit lower in its oxidation state, and then this one also has a +1 oxidation state, so carbon gets lowered down to its -4 oxidation state. So you don't need to go into this much detail with a Lewis structure. I just personally I sometimes like visualizing this for molecular compounds, how the idea of oxidation states as being a measure of electron gain or loss, rather than thinking of it exactly like a charge. This is an alternate way to think about oxidation numbers. So I'm going to erase that for the time being. Let's see if I can work through the rest of these here. So here, the net negative charge, or chlorine, again, chlorine doesn't fall into any of these categories. It's not in group 1 or 2, and it's not fluorine, so it has a variable oxidation number. It depends upon what else it's bound to. So we have to resort to rule 6 again here, and figure out the oxidation states of everything else first. So I know that the sum of the oxidation states has to be -1 because it has a net negative charge. Oxygen here should have a, I'll put it above here, a -2 oxidation state because oxygen usually has a -2 oxidation state. So I have -2 should be somehow equal to -2. Well, the only way I can do that is if chlorine has a +1 oxidation state. Then 1 minus 2 should give me -1, which is what I expect. So I would say chlorine has a +1 oxidation state in this compound. To give you guys an example, I should probably do that here. I should have done that previously, but I'll give you a different example here. This is for something slightly different compound, ClO2, which is also a perfectly stable compound. In this one, even though it's still chlorine and oxygen, you'll be able to see here that the chlorine has a different oxidation state for this molecule than it does for this molecule. I will yet again apply rule 6 and say, okay, this molecule is neutrally charged, so it has a net 0 oxidation state. The chlorine, the oxygens, there are 2 of them, and they each are providing a -2 oxidation state. So this term collectively should be -4. To get to 0, that only is going to happen if chlorine has a +4 oxidation state in this compound. So even though they're very, very similar in terms of the number of atoms, they can have drastically different oxidation states for species other than oxygen, hydrogen, or one of the alkaline or alkaline earth metals. For this one, potassium cyanide, there's a couple of ways to think about this. You could just you could go straight to rule 6, or one thing you could note is that potassium cyanide exists as a potassium ion and as a cyanide ion. So this guy has a +1 charge, and then this guy has a net negative charge. So the potassium, because it has a +1 charge, it's really a monoatomic ion. So it should have a charge or an oxidation state that's the same as its charge. So its oxidation state is +1. And then the cyanide here, it's a polyatomic ion, and neither. Oh, I apologize. That's a tricky one right there now, isn't it? So let's figure this one out and see how we can do this. So cyanide looks like this. So we have 6 shared electrons in this molecule, and the molecule has a net negative. God bless it. Oh shit.